Welcome back to another video tutorial on our short library of videos about chemical equilibria. So far we've already talked about the equilibrium constants Kc, Ksp and Kw. In this video tutorial we're going to introduce Ka and Kb and look at how we might be able to use this to determine the pH of a solution. Kw serves as an introduction to two other equilibrium constants, as I mentioned, Ka and Kb. Ka is typically used to describe how acidic a species is, and it's related to its dissociation in water. Here's the general reaction for the dissociation of an acid in water. And you can see what we have here is our acid. And I'll just turn on my little inking device here. This is our acid here, and it's dissociating in water. The products to that reaction are the conjugate base and, of course, protonated water. And here's our equilibrium expression right here. Notice that water doesn't appear in this equation. It has an activity of 1, and so it doesn't need to appear in that equation. You'll notice that the products are on top of the equation, and the reactant, the acid, is on the bottom of the equation, just like all of the other equilibria expressions we've seen. Consider a strong acid such as hydrochloric acid. You guys have used this before, and you probably know that when hydrochloric acid dissolves in water, it's a very efficient dissociation. Pretty much every single one of those molecules dissociates into H plus and Cl minus. There's not really any HCl molecules left in solution which are undissociated. So the concentration of HCl, the molecule, is very, very small. And the concentration of Cl minus and H3O plus are as large as they possibly can be, depending on the original concentration, of course. Sub these values into your Ka expression, and of course this means that Ka is going to end up being a very large number. Big numbers on top, small number on the bottom, ends up being big number, right? So that's a strong acid. But consider a weak acid, such as, in this case, I've got acetic acid. When acetic acid dissolves in water, it's actually a very inefficient dissociation. So what that means is the concentration of the undeprotonated molecule, if you like, or the undissociated molecule, it barely decreases. And the concentration of the conjugate base and H3O plus are significantly smaller than that undissociated molecule. Sub this into the equation and we should see that Ka would be much smaller than what we saw for a strong acid. Just to reiterate, these numbers up here, quite small. This number here, still quite large. In other words, Ka is going to be much smaller. Ka values are pretty well tabulated, and these are very useful values when considering the behaviour of weak acids. This brings us to Kb. Consider the reaction of the conjugate base when it's in water. There it is. Now in this case, I'm not saying that the reaction is just been flipped around. I'm saying that the conjugate base is reacting with water. Have a look at the products. The product is, of course, the acid, but in this case, the hydroxide ion. If we develop our expression for Kb, it's kind of similar to before, but a little bit different. Again, H2O doesn't appear in the equation. It's got an activity of 1, but the remainder do. Notice how the general equations for Ka and Kb both contain the acid and the conjugate base. Let's see what happens when we multiply one by the other. So Ka times Kb, and we include both of those expressions, we can actually cancel the conjugate base and the acid. In other words, Ka times Kb is the product of these two things. And I hope at this point you're thinking to yourself, hang on a sec, that looks pretty familiar. Oops, should be W. That's right, that's the expression for Kw. In other words, Ka and Kb, when multiplied by each other, will give you Kw. Well, we know Kw, 25 degrees Celsius, equals 1 times 10 to the minus 14. Looks like a pretty useful expression if you ask me. Let's do a sample problem. The Ka constant can be used to determine the pH of a solution. We'll take our good old friend here, acetic acid, which we've talked about in our example of a weak acid. And the Ka for this acid is pretty well known. What is the pH of a solution where the original concentration of acetic acid is 0.1 molar? You'll notice that the stoichiometry of this reaction is 1 to 1 to 1 to 1. Well, that's a pretty useful piece of information. The reason why is because when this species dissolves in water, these two concentrations are going to be exactly the same. So for solving this problem, let's call that X. If we rearrange our equation, actually no, I'll just write it out as it is. So we've got Ka equals, what have we got? We're just going to call the concentration of the conjugate base X. Concentration of H3O plus is also X. And we've got the concentration of the original acid. Well, we know these values. Ka is 1.8 times 10 to the minus 5. Call that X squared. The concentration of the original acid was 0.1 molar. Rearrange the equation. .3, plug that into your calculator and you should get something that looks a bit like that to two significant figures. X, we said, was both the concentration of the conjugate base and also the concentration of H3O plus. Now remember, the question asked, what is the pH of the solution? How do we work out pH? Using this equation here. Well, we've just determined H3O plus, so sub that into the equation. And if I've done my calculations correctly, you should get an answer which looks something like that. Well, that's the end of this video tutorial. There's still a couple left in this series. We're going to talk a little bit about the Henderson-Hasselbalch equation and Kp, which are used for gas phase scenarios.